Hey guys, okay, so here's topic 5, momentum and energy theory. So in this section, there's a lot of algebra that I'm not going to go over. Some of it is done, some of it's partially done in this presentation. So if you want to go through the algebra, you're welcome to. But I've tried to put the main equations in outline boxes, like you see right here in 5.1. Okay, and you can also look at the summary notes to help summarize this stuff. Don't forget the summary notes that are posted on our course webpage. Anyway, we first have to define momentum, and the derivation is not done in this PowerPoint presentation. That would involve too much time, but the result is that the momentum can be expressed as a mass times a velocity, but the mass is not what we normally think of, okay? There actually is a distinction made between what we call the rest mass of a particle or object and its relativistic mass. So the way you can view this is, if you want to use an SS prime diagram like in figure 5.1, we just have one observer now. Put that observer in frame S. The particle or object is at the origin O prime, and is moving to the right here in this picture at speed u. So you put the object in frame S prime. If you do, the reason we want to do that is we want to define a gamma factor. In fact, the gamma factor between the particle or object and the observer is what you see in 5.2. It's the regular old gamma factor, except we're using u for the velocity between the frames instead of v. If you define the gamma factor that way, the momentum, it turns out, is gamma times what's called the rest mass of the particle times the velocity. The rest mass is the mass of the particle measured when it is at rest with respect to an observer. If it's moving, however, you can think of it as having an increase in mass. So this factor of gamma multiplying the m naught, we call that the relativistic mass, and that is usually symbolized by just m. So we can write momentum as m times velocity, but that m is gamma times the rest mass. As the particle speeds up, as u gets bigger and bigger, the gamma factor gets bigger and bigger, the relativistic mass gets bigger and bigger. Okay, now notice if the velocity of the particle is much less than the speed of light, remember, the gamma factor in that case is going to be approximately 1, and this is the regular old momentum that we're used to, mass times velocity, although it would be what we would call the rest mass. In classical mechanics, non-relativistic mechanics, the rest mass is the mass when the particle is moving at any speed. It's only when you get near the speed of light that you have to worry about that increase in the relativistic mass. All right, so there's the momentum. Okay, the next thing we have to do is we have to use that definition of momentum to do the rest of mechanics. So for instance, we can look at force and acceleration. So in this slide, what we do is we consider a case, as you see over here in this figure, a constant force applied to a particle with rest mass m naught. And let's suppose that the force is applied in the direction of the velocity. So this is a one-dimensional problem. We're only going to worry about one-dimensional problems. Well, you've had physics 1, some mechanics. Newton's second law would say that net force is the change in the particle's momentum. So what you see happening in this equation right here, this 5.4, is we're putting in the relativistic expression for momentum. Then when we take the time derivative, we've got to remember that gamma also depends on time, not just the velocity, because gamma has the speed in it. So we end up doing a product rule and end up writing this equation right here. We've used the fact that du dt is the acceleration. Now what you have to do is you have to evaluate d gamma dt. And that's done using the chain rule that you see right here. Okay? Then what you do is you do some algebra, and that's what I've skipped. So you take equation 5.5 and you solve it. Well, you actually stick that into this derivative right here in 5.4, and then you solve it for a. Trust me, after a lot of algebra, you end up with a rather simple expression. It looks like this. Acceleration is force over gamma cubed m naught. In regular non-relativistic physics, it would just be F over m naught, because the gamma factor would be essentially 1, and that's what we're used to. But we find out for relativistic mechanics, the acceleration actually gets smaller and smaller and smaller, even though the force is constant as the particle speeds up. In fact, it gets smaller very quickly because this gamma factor, as you might recall, as u approaches c, the gamma factor is approaching infinity, and a depends on 1 over gamma cubed. So as this particle speeds up via this constant force, the acceleration is going closer and closer and closer to 0. In fact, if you try to make the particle reach the speed of light, it's impossible because the acceleration is going to 0. It'll continue to speed up, but the rate that it speeds up is getting less and less and less and less. So that's something you guys should remember, and that's in the summary notes. Okay, the next thing we're going to do is we're going to look at work so we can look at kinetic energy. So we're going to consider the work done by that constant force. And you guys might remember from physics 1 that the work is this integral of f dx for that 1D case. And what we're doing here is we're putting in the expression for the force that we found on the previous slide, right here. Okay, we're writing the acceleration as du dt. Then we're doing a little switch here. We're going to take this dt, and instead of dividing the du, we're going to divide the dx. That's valid because these du, dx, dt's, these are all tiny intervals. But then we say, oh, that dx dt, that is the speed u. So we end up, it's rather tricky, a nice little trick I should say, is instead of integrating over x, now we can integrate over the speed. And we're considering that this thing started at rest, and then it reaches some speed u at a later time. So we have to use this, do this integral right here. It's not that bad of an integral to do. You can do it. You can verify this. You will actually get this expression right here in 5.9. Then what we do with that is we say, we remember the work-energy theorem from physics 1, right? You all do. That says that the net work is the change in the kinetic energy. But since this particle started at rest, the initial kinetic energy is 0. So this expression right here in 5.9, that must be the kinetic energy when the particle is traveling at speed u. Look at that. So look, we just derived the relativistic expression for kinetic energy. Now we're used to 1/2 mass times speed squared. That looks nothing like it, right? I'm telling you though, in the low speed limit, if you take u a lot less than c, it will revert to that. It's sort of hard to see because you don't even see a speed in this equation, 5.10. But remember, the speed is in the gamma factor. And this is a fun one, because if you want to show that you in fact get 1/2 mass times speed squared, you can do a Taylor series expansion on that gamma function. You keep the first two terms as described here, and this will collapse into 1/2 m naught u squared when u is a lot less than c. So that's nice. Okay, next thing. We can take this equation right here in 5.10. We can actually write it like this, if we just distribute the terms. What's neat about this is, look at the right-hand side. We have a kinetic energy. That's an energy due to motion. But then we have this term, this m naught c squared, and all that depends on is the rest mass of the particle. So this is a new type of energy. We call this m naught c squared the rest energy of the particle. It is an energy that is only due to the fact that this particle was made out of matter. So if we take the sum of the rest energy and any motional energy, we're going to call that the total energy of the object or particle. So it must be that left-hand side is the total energy. If we write that total energy as E, we can identify that E is gamma m naught c squared, which is the sum of the kinetic and the rest energies. But then if you remember that we called gamma m naught the relativistic mass, plain old m, we could rewrite this equation 5.12 as a very famous equation, E equals mc squared. The importance of this idea of rest energy is that matter can be converted to energy and vice versa. That's the long-range implication. People didn't realize that until Einstein did this work, that there is an energy just because something is made out of matter. And under certain circumstances, you can actually tap into that rest energy. We'll talk about that later in the next video. Okay, one other thing we need to talk about before we leave this PowerPoint slide, and that is to review the stuff on photons, which are energy particles. We've been talking about matter particles, right? Now we're going to talk about energy particles, which are photons. So just remember, a photon does have a momentum. Now we're going to say it does not have a rest mass, but it does have a momentum. And remember, to find the momentum, you take the energy divided by c, which is the same as Planck's constant over the wavelength that you see right here in 5.16. Now what you can do, and this is something new now, and we didn't talk about before, if you want to write the momentum, you don't have to, but if you want to write the momentum of a photon as a mass times the speed of light, because momentum, right, for a matter particle is a mass, the relativistic mass, times the speed. So if you want to write the momentum of a photon, as you see in 5.17, as a mass times c, we call that mass the effective mass of the photon. And if you equate that expression for momentum with the 5.14, the one that's boxed up here, that effective mass then has to be the energy of the photon divided by c squared. So this is just, it's something extra. You don't have to do this, but a lot of physicists would do this and treat the photon as a particle with an effective mass, which is its energy over c squared. Okay, that's it for this module. This presentation. The next presentation and video, we're going to do some examples. So make sure you watch that. Bye.